Thank you very much, Konstantin. So I understand that you can see my slides, you can see me, and you can hear me. So let's start. As already mentioned, I'm going to talk about heat and charge transport in solids, and I will try to, to basically evolve this talk around really the concept of anharmonicity and how anharmonicity drives these transports. And besides introducing these concepts, I will show you how we can use established and also novel methods to address these questions and then to apply these methodologies to relevant applications. But let's now really dive into the topic. When I'm talking about heat and charge transport in solids, I really refer to a bulk material. So to really think about a big piece of bulk that is hot on one side and cold on the other, and then naturally there will be a heat flux trying to reestablish thermodynamic equilibrium. And in principle, all particles that are able to carry energy are involved. This can be photons, that can be electrons, and can be nuclei. In the exact same fashion, you can think about charge transport. You have again a big piece of bulk, and then you apply a voltage difference, and then there will be again a flux, this time a charge flux that tries to reestablish electronic equilibrium. And here all charged particles are involved. That can be electrons, that can be ions, or even polarions. So these processes are in principle related, and since electrons and ion can transport both charge and energy, you can also couple these processes. And this gives rise to this called thermoelectric effect, in which you can induce a potential gradient through a heat flux. This is called the Seebeck effect. And the inverse effect, where you use a charge flux to induce a temperature gradient, is called the Peltier effect. Now, again, remember, I'm talking here about macroscopic bulk materials. Nonetheless, the actual details and how the efficiency of these processes is determined by microscopic atomistic effects. As a matter of fact, what really is determining this transport efficiency is the nuclear motion, because the nuclei continuously move even at 0K, and with that they disturb this flux, they disturb energy and charge dissipation and cause friction. In turn, on a macroscopic level, this gives rise to this kind of transport equation, Fourier's law for the heat that relates the heat flux to the temperature gradient, and Ohm's law for the charge case, where the flux is related to the potential gradient. And this constant sigma, the electrical conductivity, and kappa, the thermal conductivity, is exactly what we want to calculate out from simulations of these nuclear motions. And this is exactly what this talk is about. How can we start from this microscopic picture, extract information, and then bring that up to scale to really describe macroscopic material properties? Now, to make the problem a little bit simple in the beginning, I will focus on heat transport at first, so that we can stick to that, and we will get to the charge transport later. We will make the problem even simpler. As said before, we have photons, electrons, and nuclei involved in heat transport, and at first we neglect the photons. These are only relevant in transparent, incandescent, so glowing materials where really you have a lot of photons being sent out. So that is not the usual case, so we neglect that. Similarly, we neglect the electrons. They play a role in metals and degenerate semiconductors, and we will discuss them later when coming to the charge transport. What we're left with are exactly the nuclei, the nuclear motion that is, and this is the dominant contribution in insulators and non-degenerate semiconductors. Now you might think that I have oversimplified this problem already, but this is not true. Even just explaining the lattice thermal conductivity in insulators and non-degenerate semiconductors is a formidable problem with a lot of applications. Think, for instance, about semiconductor technology. What happened over the year, if you look at this first CPU that I actually ever used and compare it to what you can get today, there has been an increase in 4 orders of magnitude in the number of transistor densities, without the CPUs increasing by 4 orders of magnitude in size. So we have a massive miniaturization, And this leads to local hotspots at the nanoscale. So really the CPU gets hot, but really on nanometer sized regions. And it is extremely important to get rid of this heat as fast as possible, as efficiently as possible, to increase the lifetime and increase the efficiency of next generation CPUs. So here, this is an example where we really have to increase lattice thermal conductivity in such materials. Converse example would be thermal barrier coatings, which are used in turbine technologies, for instance in airplane turbines. Here, a minute layer of the ceramics, typically zirconia based, is placed on top of the superalloys that the blades are made of. And this extremely insulating material basically insulates away something like 500 K within half a millimeter, protects the underlying superalloy from the extreme temperatures generated during combustion. Now, again, this increases the longevity of such a turbine, but it also allows to increase fuel efficiency. For each 100 K you increase the combustion temperature, you roughly save 1% of fuel. And this is one technique that has increased the fuel efficiency in turbines over the last 30 years. And we want to go even further. As a matter of fact, even nowadays, each airplane you ride is actually burning its fuel at a temperature that is roughly 300 K above the melting temperature of this superalloy here. And the only thing preventing this alloy to melt is this half a millimeter of zirconia. Last but not least, let me go back to the thermoelectric effect. As mentioned before, this allows to convert a temperature gradient into an electric current. And this can have a myriad of useful applications whenever you have wasted heat that is unused and that could be transformed back to a useful current. Think about industrial plants, think about large-scale furnaces, for instance, for solid waste, but also your furnace at home, and even down to the more miniaturized scale about personal computing, mobile phones that generate waste heat that could be used to recharge your battery. Now, these are wonderful applications. However, thermoelectric materials are so far too inefficient to allow for a large-scale, economically attractive or viable deployment. So also here, we need to develop better thermoelectric materials to make such applications possible. And the route we can contribute to this from a point of view of a theory is to really start understanding the nuclear dynamics in these materials and then to be able to then tailor and improve the thermal conductivity. So to understand nuclear dynamics in solids, one typically starts with this kind of pictures. One has a real space representation of the potential energy surface for the nuclei with a certain equilibrium. And then one expands the potential energy surface around equilibrium in a harmonic approximation in a second order Taylor expansion. This gives rise to the concept of phonons, this nice phonon band structure in a reciprocal space. And this is an extremely successful and extremely elegant and extremely numerically efficient approximation because we're dealing with decoupled modes that allows us to deal with these modes separately. However, due to the fact that these modes are decoupled, they result in phonons that do not see each other. And this results in infinite lifetimes. Accordingly, phonon package can travel through the bulk without any friction. And this results in an infinite thermal conductivity. So to really heat transport, we have to go one step beyond and account for anharmonic effects. Now, one way to do is to do that via perturbation theory to basically allow for small perturbations here. In perturbation theory, this gives then rise to scattering effects. Since the phonons start to see each other, you can have phonon creation and annihilation processes. And if you put this kind of cross-section into perturbation theory, you can then put that even in further transport equations, and you get very nice thermal conductivities calculated out of that. This works very well for many materials, but you have to keep in mind that this is a low temperature approximation. Essentially, what you're assuming is that the harmonic picture is valid and that all the anharmonicity is just a small, minor disturbance on top of it. This might very well hold in this example showcased here by the green arrow, but if you go to either higher temperature or just materials with a more corrugated potential energy surface that have a more complex dynamics, where you overcome barriers, explore minima, break bonds, this is no longer an appropriate approximation. And this is what we will be treating here, where exactly this perturbation theory starts to fail, because you can no longer treat anharmonicity as a perturbation, because it becomes as strong or even stronger as the actual harmonic effects. Now, uh, this is an appealing picture, but to get there, we have to first really understand what anharmonicity is. First, we stick for one more slide to this PowerPoint science, where I'm just telling you, it's easy to understand here that this obviously would be a system where the harmonic approximation is valid. Here we have a little bit more disturbances. Here we get massive problems if we overcome the barrier. And here we have imaginary frequencies, so the dynamics would never be described by a harmonic approximation at that thing. So how can we translate this kind of intuitive PowerPoint physics into material science that we can use? Can we quantify an harmonicity material space using such a logic? And we've recently, a couple of years ago today, together with Florian, developed an anharmonicity quantification metric and toolkit that is relatively intuitive and follows the arguments that I had so far. Practice, we just run up initial molecular dynamics, so fully anharmonic. We store the trajectories, we store the energies along this molecular dynamics, and then later on we evaluate what the harmonic approximation would have predicted along these positions. And by then looking at the differences and comparing that by building the average, thermodynamic average along this trajectory, we can get a feeling how anharmonic the system is. In practice, we do that with forces and not with energies, just because we get more information out of it. We get an atomistic resolution naturally from the forces. This you see, for instance, in this kind of correlation plots, where I show the DFT forces and compare them to what the harmonic forces would have predicted for silicon at 300 K, so at room temperature. And you see there is a very nice correlation here, and this implies that this, as very well known for silicon, is a well-behaved harmonic material. Another example, here copper iodide at 300 K, similar simple material, zinc blended structure, again room temperature, shows quite a different behavior. Not only is this distribution broader, here there are even points where harmonic and anharmonic forces point in different directions. Here or down here, for instance. In turn, and we will discuss that further also in the course of this talk, this hints that we have here very anharmonic material in which different minimas are explored. To quantify that more in a single number that you can use as guidance, we proposed an anharmonicity metric. Essentially, this is nothing else than the standard deviation of this distribution. Here, this would be 0.15, and thermodynamically, this implies that 15% of the forces on thermodynamic average stem from anharmonic effects. So a small amount, so here perturbation theory is certainly justified. Copper iodide, on the other hand, gives you such a sigma metric of 0.5, implying that 50% of the forces on average stem from anharmonic effects. Here, surely we have a material where perturbation theory comes to its limits. Apologies. So, and this leads me already to my first take-home message. If you're interested about quantifying the strength of anharmonic effects, use ab initio molecular dynamics to explore the phase space, and then you can use such matrices or similar concept to quantify how anharmonic this material is. Now, this brings already to the next question. So if this system is so anharmonic, what are the implications for thermal conductivity predictions? Now, for this kind of system, there are both experimental results and literature theory using perturbation theory for the thermal conductivity. And you see quite a large disagreement, almost 350% of disagreement. And so to understand this material, we obviously have to go to a theory that is better than perturbation theory and that accounts for the anharmonic effects. And for that, we've developed a couple of years ago an ab initio version of the Green-Kubo method. The Kubo method is based on the fluctuation dissipation theorem, and it uses simulation of thermodynamic equilibrium to infer about the transport in non-equilibrium processes. In practices, this implies that we have to run ab initio molecular dynamics, calculate the heat flux, then its autocorrelation function over time, and the integral over it gives us the thermal conductivity. Now, conceptually or formally, this has several advantages. Since the Green-Kubo method works in thermal equilibrium, we don't have to explicitly include non-equilibrium like temperature gradients, which would be quite problematic in the finite supercells that we typically use for first principle calculations. Furthermore, the Green-Kubo method accounts for all anharmonic effects because everything is based on molecular dynamics, so the complete dynamics is included. However, this method also faces severe conceptual and numerical challenges. I will shortly touch about the conceptual one, and you will learn more about the numerical challenges tomorrow in the tutorial. Conceptually, we need to define a heat flux. So, the atomistic heat flux by itself is defined with a continuity equation that relates the local heat flux density to the local energy density. Integrating that up then gives you the complete heat flux. One can, for instance, assume that each individual atom carries a certain amount of energy and assign this to that position. If you use this kind of formula and then integrate these equations up, you end up with this quite insightful equation already, in which the heat flux is defined as the time derivative of the energy barycenter. This looks nice as first, however, please be reminded that energies are not well defined. Even in a pairwise potential, it is not clear if each of the two involved atoms would get half of the energy, or is it 1/3, 2/3? How does that change? And this gets even worse in first principle methods, where we typically don't have access to these individual energies in a consistent fashion. In other words, the energy is by itself not Gaussian invariant. So to overcome or better circumvent this problem, what we've done is to take this time derivative inside, and then we get two terms. The first term, velocity times energy, describes convection. This is important in liquid and gases, where, for instance, a molecule carries a certain amount of energy, it flies through the room and brings that energy to another place. In solids, where typically diffusion is negligible, if diffusion is negligible, there is no mass transport, so we can also neglect this convection part. Then we're left with the second term, which only involves time derivatives of this energy. Now, time derivatives of the energies can be recasted as forces, and forces are Gaussian invariant, they're unique, they do not depend on the partitioning. You can map them exactly to phonon transport. They're well defined for classical potentials, for machine learning potentials, and even in first principle frameworks. So we can really calculate that from first principles. And without spending more time really on the fundamentals, let's really look what is the impact on actual materials. If we now do this for copper iodide, what you see is we get a result even using the exact same electronic structure theory settings from K points to sizes to exchange correlation function, and we get a result that is much closer to experiment. So we really start to get into a regime where we are predictive even for such strongly anharmonic insulating materials, where perturbation theory obviously is not sufficient. This brings me to my second take-home message. The developed and implemented ab initio Green-Kubo method now allows you to describe lattice thermal conductivity, and that not only for very harmonic systems, but even for such strongly anharmonic systems. Now, naturally, this example begs the question, what is actually happening at an atomistic level? So why is this so much difference? We've seen that this has to do with anharmonicity, but can we get more fundamental, more qualitative insights that explain what is going on? And one way to do that is to map that back into a quasi-particle phonon picture. So what we do here, so what I show you is the lifetimes, or better the inverse lifetimes of these phonons as a function of their frequency. And this data is completely extracted from the ab initio MD. So accounts for all anharmonic effects. Now, there's a very nice theory or a theorem, the Joffe-Regel limit, that tells you that any quasi-particle excitation, so any quasi-particle like phonons or excitons and so on, to be to be meaningful, must have a lifetime that is larger than its 1 over its energy or 1 over its frequency or its oscillation period. I mean, that is quite easily understandable. If you have an oscillation that does not even survive for full oscillation period, it's hard to talk about an oscillation at all. And indeed, here in copper iodide, we see that there are many, especially these low frequency phonons. These are valid phonons. These have all lifetimes that are longer than their actual oscillation period. However, in copper iodide, we also have some phonons, and not just one, that lie beyond this limit and that fall into this strongly anharmonic regime that lies beyond the phonon picture, where the phonon picture becomes invalid. And this is the reason that perturbation theory, which fundamentally relies on a description of the dynamics in terms of phonons, is no longer applicable for this material. Now, this is basically a many-body perturbation theory picture of this physics. You can even get, for me, more intuitive real space insight what is going on. Here we plot the anharmonicity metric for this material as function of time along one of these trajectories that we computed. And you see that for a very long time we see this typically anharmonicity metric of 0.5, and this happens for a long time. Then sometimes you see little jumps and then it goes back to its original value. If we look at this blue regime and just average the structure, we indeed find a pristine zinc blended structure of copper iodide. However, here where this jump is, where the harmonicity matrix goes to 1.2, which implies that actually anharmonic forces and harmonics point in different directions, if we take this structure, we see that here actually a Frankel defect has formed, so a vacancy self-interstitial pair has formed here for the copper iodide. This spontaneously is created. It survives for a couple of picoseconds before it decays again back to equilibrium. Now, here, what we observe is exactly what I discussed before. We have explored another minimum. We were stable therein for a while, and this has disrupted our nuclear dynamics, leading to this breakdown of the phonon picture. Eventually, let me just show you that actually this Green-Kubo method does not only work for copper iodide. You can indeed benchmark it across material space. Here we've done something like 30 plus materials for which relatively well measured experimental data was available, ranging from up to almost 100 watt per meter Kelvin down to less than 1 watt per meter Kelvin, so over 2 orders of magnitude. And you see that our calculations and experimental value are in very nice agreement in the range, the mean absolute percentage error of 25%. Also, experiment is not that much better, I would say, in many cases. And especially here in this low thermal conductivity range, here you see our copper iodide again, for instance, we have a mean absolute error of only 1 watt per meter Kelvin, which is really, really nice and satisfactory. So, to wrap up this whole lattice thermal conductivity discussion, let me remind you that this local and or temporary distortion can break this Joffe-Regel limit, lead to a breakdown of the phonon picture, and with that to a breakdown of all these perturbative frameworks. So here you have really strongly anharmonic materials that need more advanced methods to be treated. Now, if you have such breakdowns, then question naturally arises, what about electrons and charge transport? Can we incorporate this kind of effects also in our calculations for electron and charge? And to understand what is going on there, we first have to explore again what is typically done and what one can do and where the approximations are. And for electron phonon or vibronic coupling, so electronic and vibrational coupling, one typically also uses traditional perturbation theory. And that implies that one That's again what we've discussed before. One approximates the potential energy surface by a harmonic approximation, and this basically captures all the nuclear motion. But if we're interested in vibronic effects, we also need an additional term for the electrons. This means that the wave function, better the dependence of the wave function on these harmonic displacements, is also described using a Taylor expansion around this equilibrium. So one goes to first order and describes the response in terms of this expansion coefficients, electron phonon coupling elements. Again, this works very well for well-behaved materials, but you can also see that materials where the Joffre-Regel limit breaks, so harmonic approximation breaks, also will not easily be describable with a linear expansion of the wave function. So what we do here to overcome these approximations is to get rid of the harmonic one. That is clear. So we do full exploration of the past by ab initio molecular dynamics. But to then tackle also the electronic part, we rely on the self-consistent wave function. If we anyhow do ab initio molecular dynamics, we solve the Kohn-Schramm problem at each of these points anyhow. So we have these self-consistent wave functions ready. Still, to better match back to equilibrium, we do a similar expansion as done in perturbation theory, but without an approximation. We do not do a Taylor expansion, but rather project these individual self-consistent wave functions back to equilibrium and then get this kind of expansion coefficients that are not constant like in the case of perturbation theory, but are highly nonlinear functions of the actual nuclear positions. At first, you might think why this is useful, and this becomes clear in a second if you think why and how what these things describe. When doing periodic calculations, we typically describe the electronic structure in terms of band structure, like here for the primitive cell. If we go to larger cells, however, the Brillouin zone gets smaller. It gets folded. So essentially this is mapped back and you get to larger and larger Brillouin zones. You get denser and denser band structures. And it becomes very complicated to get a qualitative interpretation of what is going on if everything starts getting folded back. This process called Brillouin folding is exactly what is undone by our band structure unfolding by these coefficients here. So by projecting on the equilibrium functions of the unit cell, of the primitive unit cell, we can restore a picture in the fundamental Brillouin zone that allows a more intuitive and quantitative interpretation of the results. To give you an example, if I now would run calculations in these three different supercells, I would get the exact same band structure by the means of such an unfolding technique. It becomes more interesting, however, if we don't look just at a supercell that is in perfect equilibrium, but if we start distorting the atoms in the supercell. Then we break translational symmetry, and when mapping back, we no longer get a perfect mapping. Rather, the electronic states get smeared out and we get a kind of weighted distribution. This is nothing else than the electronic self-energy renormalized by vibronic coupling for one configuration. And if we then perform a thermodynamic average over all such unfolded band structure in an ab initio MD run, we then get the temperature dependence of the spectral function or of the electronic band structure in thermodynamic equilibrium. Just a simple example here as a validation that is often used in this field. This is silicon in a relatively large supercell, and you see in black the original band structure at 0K. And you see now in our calculations the level have shifted and the level have broadened since we now have no sharp electronic structure anymore, but rather distribution. This is a nice demonstration, and one can compare to literature and validate the involved methodology. But it becomes more interesting if we go to anharmonic system. Here we have looked at strontium titanate, a perovskite, that is stable in that tetragonal structure at very low temperature, but is then only dynamically stabilized. So it's such a system with a double well or multiple well potential like here at room temperatures and higher. And the interesting thing about this material, besides being important for many applications, is that it has a pronounced dependence of the electronic structure, here the band gap, as a function of temperature. These are experimental results up to very high temperatures, and they show a massive renormalization, a massive change of the electronic structure and of the band gap with temperature, up to 1 eV and more if you get to really 1000 Kelvin and more. If we try to assess this behavior now using standard perturbation theory, so what I described before using harmonic approximation and electron photon coupling coefficients, we get very nice results here in the low temperature regime. We even capture the quantum mechanical effects at 0K that can only be captured with a quantum mechanical theory of phonons. But for larger temperatures, we see a slope of this band gap that does not agree with experiment. If we now switch to a fully anharmonic method, let me mention in passing that longer range effects are accounted for using a Friedrich coupling term. We see a much better agreement with experiment. We get much closer to the actual slope. Naturally, since we're using ab initio MD, we cannot capture this low temperature regime because these quantum nuclear effects are not captured. But here, this high temperature regime is really captured well. So this shows you that using this unfolding technique and coupling it to statistic anharmonic higher order approaches gives you the potential to get predictive calculations of electronic properties. And we can not only look at electronic properties, we can also look at actually linear response with that. And for calculating electronic transport coefficients, we use, in analogy to what we have done with for the lattice thermal conductivity, we use here the Kubo-Greenwood formalism. This is again based on Kubo's linear response theory, here in its quantum mechanical formulation in terms of trace and density operators. And this gives you the frequency-dependent conductivity. And if we then use an independent particle picture as done in density functional theory, write up out the flux operator in such a picture, and then transform it in a Heisenberg operator and evaluate this kind of equation, what we get is this kind of equation describing the frequency-dependent conductivity. Now let me just point what this actually describes. You see here we're describing transitions between an electronic state N and an electronic state M that differ by an energy amount of h bar omega. These are dipole transitions, so this transition probability is given by this dipole operator, and obviously transition can only happen from a partially occupied to a partially unoccupied state, but not between two fully occupied or two fully unoccupied states. This is what these occupation numbers give here. And this has to be evaluated in thermodynamic equilibrium. And most importantly, if we want to calculate transport coefficients, we want the limit of omega equals 0. So without external stimuli, but just in the linear response regime. How does an evaluation of this equation look in practice? Here, a toy model, a simple aluminum system. If you evaluate this, what you see is along this kind of band structure that we see peaks whenever we have an h bar omega that essentially matches up with a certain distance in this kind of band structure. So here for this blue, we have this peak at 10 eV, and then here later on, this orange peaks here. However, we have no peaks here in the low frequency region because there's always there is no transition between unoccupied and occupied states that is possible in this energy window. This is also clear, we're only describing direct transitions, and if we want to describe electronic transport, we need indirect transitions, so transitions from one K point to another. So non-vertical transitions are required that couple to the phonons. This can be realized in a supercell. Just doubling the supercell does not help though. You do not change the symmetry, so you get the exact same result in the doubled supercell as you would get in the primitive. If, however, you start introducing displacements, you start breaking the symmetry, and now naturally transitions become possible. For instance, here, really at the Fermi level here, and this leads to an exponential increase in intensity here in the low frequency regime. Note that here I'm using a logarithmic scale, and here it was a linear. So it really massively goes on. And again, for this toy system, you can look really at how this would look like, just moving one plane of this aluminum back and forth, and you see how the electronic structure changes, opens up, how new transitions are introduced, and then by averaging over this kind of conductivities and going to the zero frequency limit, you can obtain the conductivity. Now,
hey, Christian, roughly 2 minutes, 3 minutes,
yeah,
if possible.
that should work. So let me just quickly glimpse over that then. As said, evaluating this equation for a toy model is easy. In practice, converting this is really challenging. First, you need extremely dense K-grid to resolve this zero frequency limit. This can be resolved with Fourier interpolation. You can read more about that in the paper actually here. But you also need large supercells to resolve the phonon dispersion. And this requires an extrapolation to the bulk limit. Here, practical example for strontium titanate again. If you have a very small supercell, 2 by 2 by 2, you get a maximum here. If you get to larger supercell, this gives you maximums closer to the zero frequency limit, but not perfect. The reason can again be found in this unfolding. If you think about in the primitive cell and just think about a certain frequency, the only transition that is possible is here. In the folded structure, you get immediately more transitions that become possible, and the more you fold this, the more effects you get. And by then fitting this kind of behavior over different supercells to a Drude function, you can really then extrapolate actually to the Drude limit that is then gives you access to the zero frequency conductivity. So far so good on the methodology. Let me just showcase the results from Jinquai that I currently impress. Now, if we try to model the mobility in highly anharmonic strontium titanate, if you use standard perturbative approaches, even with the normalized phonons, you would end up roughly an order of magnitude too high in mobility. This can be reduced by using more involved approaches that include higher order effects like a cumulant approach. Then you end up here. But still, perturbation theory would involve a 1 over T behavior of this conductivity. If you apply fully anharmonic Kubo-Greenwood theory, you can not only reproduce what happens down here at this low temperature regime, you can also go to this high temperature regime where we observe basically a deviance of this 1 over T behavior. And again, this is a nice result because we can now qualitatively reproduce actually what is happening in experiment, and we can even explain it. For that, we can go back to our folding strategy here now for the strontium titanate, and you can then map back to seeing that you see a flattening of the group velocity, a reduction of the phonon lifetimes, and that really describes this kind of behavior in this high temperature regime. And with that, this leads me to my last slides. The non-perturbative Kuhn-Gruber-Grimm moment shows you that you can now also do predictive calculations for electronic conductivities in anharmonic materials. Let me rapidly thank people involved in this project. This is obviously Matthias in the department of which I've done this work over the last years, and they basically postdocs and PhDs that were involved. That is mainly Florian for all the thermal conductivity benchmarking and the copper iodide example, Marius for the unfolding, and also Jinkai, and then Jinkai for the Kubo-Greenwood method. And let me emphasize, Shuo is working on thermal conductivity, and Shuo and Jinkai are really the ones that prepared all these nice tutorials for you tomorrow. So they have done excellent work and put in a lot of effort to prepare something that is easily doable, understandable, and can guide you more into the intricacies of that method. And with that, I'm looking forward to your questions.
Thank you, Christian, also for your talk. Again, some nice claps in the audience. So they also enjoyed. As before, I would now hand over to James to handle the Q&A session. So James, please.
Thank you, Konstantin, and thank you, Christian, for the talk. And yeah, the questions are already appearing in the chat, in the Q&A, sorry. So we have the first one from Shubham. How should the coupling term be considered when evaluating kappa L, for example, EE, EP, and PP?
We have to look at the question myself because it's not really clear what this meant, to be honest. Can I see what this? I'm trying to read it now in the Q&A. Okay. I mean, I understand the question now. Yes, I mean, you are referring to basically looking both at electron-electron, electron-phonon, and electron and phonon-phonon coupling. What one usually would do is use basically just use a parallel resistance law, Mathison's rule that tells you that principle this kind of resistances add up. This is obviously an approximation. It's the best what we can do now at the moment. So you add basically this up as 1 over kappa complete is 1 over kappa EE, PP, EP. Typically or often this is good enough. If you would really like to do something more involved, this would imply to go to non-adiabatic systems, really doing explicit electron dynamics and nuclear dynamics, and that can become expensive for everything that is not a toy system.
Thank you. So next question, another one from Robert. So do you have a numerical experience or theory to guide whether at temperatures of around 2000 Kelvin, if most materials enter a non-perturbative anharmonic regime a priori?
So in the paper mentioned here in the very beginning, this on the anharmonicity metric, we have done some scanning over material space. I think it was something like 200 materials that we explored at different temperatures. So far from exhaustive. But what this kind of exploration has shown that already at 700 K, many materials become very anharmonic or quite anharmonic. So I would say at 2000 K, I mean, if you don't have a very particularly special material, I'm pretty sure that it will be strongly anharmonic at 2000 K. And harmonic behavior would be rather exceptional.
Thank you. So next question, for materials where the E-harms or harmonic energy is roughly equal to the anharmonic energy, are there specific properties or conditions that minimize anharmonic effects?
I'm not 100% sure if I understand the question completely. If the specific property conditions refer to thermodynamic conditions, I mean, obviously, you can cool down the system and then you will have less motion, and then it will be probably more harmonic and less anharmonic. But that will really very much depend on the material. If you've seen strontium titanate, it becomes strongly anharmonic at 100 K. So there is not much you can do there in terms of cooling down anymore.
Okay, thank you. So next question. So I'm sorry if I've missed it, but is it possible to use these concepts to evaluate thermal conductivity in metallic systems where the electronic contribution is relevant?
Yes, in principle, yes. And sorry, it was not you being missing it. It was me being a little bit fast on the last slides. Yes, in principle, you can calculate the thermal conductivity in metals for both nuclear and electronic. And for the electronic part, you can use exactly the Kubo-Greenwood method that I've showcased there. It works in the exact same fashion also to calculate the contribution to the lattice thermal conductivity from electrons. It needs just a little bit of adaptations in the actual formula, but it's conceptually and formally the same.
Okay, thank you. So next I have two questions from Ashish. So first question, could you please comment on how the low value of calculated thermal conductivity 1.38 compared to the experimental value of 1.68. Typically, we would expect the calculated thermal conductivity to be higher than the experimental value due to the idealized nature of the crystal in simulations.
I mean, to be honest, yes, that could be the case. You have to be aware, though, that the error bar in that kind of experiment also is plus minus 1 watt per meter Kelvin. And I think there are two experiments for copper iodide that we use to get this kind of result. I think we're speaking about regions of accuracy here where we would have to go beyond all kind of density functional theory if we really want to go to that kind of digits and accuracy at the 0.1 watt per meter Kelvin level. I mean, I'm pretty sure that maybe if I use another exchange correlation function and I end up maybe at 1.7 watt per meter Kelvin, and then I would maybe be closer, or maybe I can even get 1.2. I mean, that is within the variance. I mean, it's numerical theories. It's not an exact answer to the full problem.
Okay. And so the second question is, how accurate is ab initio green Kubo in estimating the thermal conductivity for materials with a high thermal conductivity?
It's equally accurate. It is typically not necessary, though. I mean, just running the ab initio MD is usually more expensive than doing a perturbative approach. Let me come back to that in a second. But in that case, something like an ab initio green Kubo approach would yield the exact same like a perturbative approach or anything else. So, I mean, it would also yield accurate result, but would be much more costly. In general, I mean, in terms of costs, you have to always compare what kind of system you're dealing with. If you have high symmetry, simple systems, 2 atoms per unit cell, then that's the regime where perturbation theory shines. If you think about more complex system, let's say with 20, 30, 40 atoms in the unit cell already, I'm not sure if you can apply perturbation theory, and if you can, I doubt that it will be cheaper than running an ab initio MD for 20, 30 picoseconds. So this depends very much also on your system.
Okay, thank you. Answered the question. So there was, just to broadcast to everybody, there was also a question about where these talks will be hosted somewhere for our repeat viewing, which Constantine typed the answer to. And these talks will be available on our YouTube channel. So if you want to rewatch anything, then you can do that. Okay, next question to Christian, then from Rocco. So are the green Kubo or Kubo Greenwood approaches feasible to capture also the defect-induced contribution to resistivity, either thermal or electric?
In principle, this is not a problem at all. So formally, it's no problem. It involves more calculations. If we want to model a defect, we have to use the respective supercell, make sure that the defect and the defect concentration is well modeled in that supercell, and then it would capture these effects naturally without any further theoretical ado, correction terms, and so on. So this would be naturally captured.
So next question, what's the difference between Kubo-Greenwood method and EPW code for mobility, electronic conductivity, and electronic thermal conductivity?
Yes, I mean, that is in principle, I might even go back to the slide to make that clearer. Just give me a second. I'm there, too many slides today, so this needs a lot of scrolling, but here I am. So EPW is essentially what we call perturbation theory. It's electron phonon perturbation theory in a many-body form. It does what is done here on the left. So it's harmonic approximation for the nuclei and electron phonon coupling expansions, coefficients here for the wave functions. There are more details to it, how this is done exactly in EPW with linearization and going to second order to some terms here, but this is basically the idea. And what we have done here with the Kubo-Greenwood theory is to fully anharmonic potential energy surfaces with ab initio molecular dynamics and self-consistent solutions of the wave function. So all the approximations that are in EPW are lifted in the Kubo-Greenwood method.
Okay, thank you. That answers the question. So, next question from Arul. Will this method have any advantage over calculating the thermal conductivity for a defect system, say a dope system? So using a frozen phonon method is formidably harder for such a system, as far as they know. Can you also comment on the application of this method on low-dimensional systems?
I mean, defected system, and this is somehow what I implied before. This is a nice thing about this kind of ab initio MD approaches. In a defected system, you can just run your ab initio MD. Ab initio MD does not take care about that, so you start. You can include it without any problems. Still, it will be expensive, but it will not face the conceptual challenges of a frozen phonon or perturbative theory method that naturally somehow requires some symmetry inside to even describe phonon dispersions and so on. And on the low-dimensional system, sorry, before I forget, fortunately, I cannot really comment of that. I've never done low-dimensional system with this method. I would expect that it should work. I have no idea how expensive it is though. Just for the exact same reason that I've mentioned before. Low-dimensional systems like graphene have typically high symmetry. You have long wavelength, long range stuff. So this kind of approaches would work, but would be probably quite expensive.
Thank you, Christian. Hope that answers the question, Errol. So now another question from Robert. So given green Kubo to describe the anharmonicity, even in the strong case, is the accuracy limiting the quality of the answer purely the electronic Hamiltonian? So kind of the level of theory, quantum chemistry that you're using.
For sure, DFT, RPA, and so on plays a role. Then there are other stuff coming in. We're doing classical molecular dynamics. There are some quantum mechanical effects going in that. Now you've seen we have typically gone to temperatures beyond room temperature or even higher, where this kind of effects play a smaller role still. There can be some small quantum mechanical effect surviving. Then we're doing numerics. Here we're doing molecular dynamics. We have a finite time step. We have a finite K-grid. We have a finite basis set. We all try to converge that out as good as we can, but there will be always some kind of a small error remaining that we try to control as best as possible. But I think and we can never go down to the, let's say, 8-digit inaccuracy for such complex material properties.
Last question in the Q&A at the moment is, I noticed a large discrepancy of the band gap renormalization between AHC theory and your method. Is there any general idea in what situation a large discrepancy like this could happen?
Yes, I mean, as I tried to explain, Allen-Heine theory actually relies on harmonic phonons. And if your harmonic phonons break down, like here in Kubik's strontium titanate, we have strong anharmonicity. Starting at 100K, you see that this strong anharmonicity appears, and then Allen-Heine theory is no longer really appropriate because you're no longer describing the real dynamics of the system. And then you need to use a fully anharmonic method to get the right result.
Okay, and hopefully that answers the question. And I don't see any other questions in the Q&A at the moment. I don't think we have any in YouTube or Kusha. So Okay. One final question just popped up. So is it possible to calculate the relaxation time?
Yes, I think for the phonons we really showed relaxation time. So I called them phonon lifetimes because they're fully anharmonic and not just a relaxation time in the sense of a Boltzmann transport. I think we showed that for the copper iodide. We had this very nice plot here where you see this is the phonon lifetime that in the limit of low anharmonicity reduces to a relaxation time. Here you see the white points are directly extracted from ab initio MD and then we interpolate to a dense Brillouin zone grid that gives these gray smaller points. And you can in principle do the exact same for electronic transport. Let me go back. Here, for instance, for silicon, here the relaxation time or the quasi-particle lifetime would be the width of this distribution here for the electrons. So you see here we have a larger width that implies a shorter lifetime because width and lifetime are related by 1/.
Okay. And then I think that is all the time we have for questions. So thank you for everybody who got involved with the discussion. If you have any further questions, then you can write to us or the speakers. And I think I'll hand over to Konstantin now to close the webinar.